priority. And we'd be very grateful for feedback on Twitter using the hashtag C3T.
Promoviert gerade beim DESI-Zentrum in Zeuthen. Das
So
ist
we are
bei der
honored
großen
to
Stadt
present.
in Berlin,
Whom do we
oder
present?
bei Berlin. Der Titel ist Kosmische Teilchenbeschleuniger und ihre Spuren in der Antarktis.
So this talk is about cosmic
Dein Applaus,
particles and their
deine
traces
Bühne,
in the
wir hören
Antarctic,
uns gleich.
and that is by Annie. Okay, she's at DESI in Zeuthen. She's a doctoral student there.
Wunderbar, dann erstmal danke
Wonderful.
Henning für die traumhafte
Thanks,
Ansage.
Henning,
Wenn
for
dann
the
keine
introduction.
Fragen sind, stelle ich einfach
Hopefully.
4 Fragen, um zu kontrollieren, ob du es verstanden hast.
So yeah, I'll ask you questions if you've
Damit
understood it.
herzlich willkommen zu meinem Vortrag.
Welcome to the talk
Kosmische
about
Teilchenbeschleuniger und ihre
cosmic
Spuren in der Antarktis.
particle accelerators and their traces in the
Ihr wundert euch,
Antarctic.
da unten stehen 2 Namen. Das ist
Down there
der
are
erste Grund,
2
warum ich
names,
diesen
which is the
Vortrag
first reason
halte.
why I give that talk.
Eigentlich ist der Vortrag meines Kollegen, der allerdings vor
It's
2,5
the talk
Wochen festgestellt
by
hat,
my
dass er leider in
colleague,
Shanghai ist.
but he noticed that he's in Shanghai right now. He's been Shanghai. The second reason, the biggest reason for this talk is that this year there was a great breakthrough in astroparticle physics in my field of research. Last year, I don't know if you all noticed, the first time there were gravitational waves were detected from the collision of 2 neutron stars. This year, it's made the big news. For the first time, it was possible to detect an ice cube, a neutrino with the ice cube detector, because that's really a big thing for us. I want to explain you what this development was, how we got there, and mostly why this is so exciting, why we are all so proud of it. The first reason where we are also proud is because everything started for over 100 years ago with Victor Hess, which detected altitude radiation in the beginning of the 20th century. We could be aware that radioactivity was a big thing back then. It was researched, and when people researched radioactivity, they wanted also to examine how our Earth would be radioactive and radiate radioactive rays. So there's mostly from decay series from thorium and uranium. And Victor Hess had the objective to detect the decay of radioactivity with altitude. And he wanted to fly up in a balloon and detect the decay of radiation from the Earth. And he wanted to detect how ionized the air is, and as a secondary signature of radiation.
Victor Hess
did that, did balloon flights. You see him in the picture. On the translations, you already see letters and... Okay, the B's are picture references and the R are probably literature references. So in the bottom right corner, everything is properly cited. So all the references are open access, and you can get further information by tracking down the references in the bottom right corner.
Okay, zurück zu Victor Hess.
Back to Victor Hess. Victor Hess did balloon flights, and he noticed that the radioactivity, first of all, the radioactivity decays with altitude, but then it increases. The further he went up above a certain altitude, the air was ionized stronger. At 10,000 meters altitude, it was a factor of 40 up. And Victor thought, am I stupid? So this radiation that ionizes the air, the atmosphere, must come from space. And that was his discovery of cosmic rays. And at that time it was altitude rays. And when he noticed that there are cosmic particles that impact on our Earth and ionize the air, we ask ourselves, well, where does it come from? What is that cosmic radiation?
Also es
And
gibt tatsächlich noch Ballonexperimente.
today there are still balloon experiments,
Aber ein gleiches Schicksal ereignet wie
but
AMS hier links oben. Es wurde nämlich auf
the
die
balloon
internationale
experiment
Raumstation ISS
suffered the same
transportiert.
fate as this AMS satellite. It was transported to the International Space Station.
Misst man hauptsächlich
At low
im Weltall
energies,
selber.
you measure in space itself because it's practical and you can measure all the time and you don't have to launch balloons, weird balloons, and
Diese Teilchendetektoren
That's up.
sehen
these particle detectors
zum Beispiel jetzt hier
look
AMS
like this. This is the AMS satellite that's on the International Space Station. Those are the particle detectors, you know, from the particle physics, like Large Hadron Collider. They're built modularly. There is one part that is measuring velocity, a part that measures velocity again. Momentum. And the core is a magnet with it's a tracking detector that detects detects charged particles in the magnetic field, and the amount of the curvature of the deflection lets you determine the energy and the momentum. And at the bottom there is an electromagnetic calorimeter that stops the particles and measures the energy, not just the momentum. And we get to the next point: why can't we use satellites everywhere? At higher energies, just the particles don't get stopped in the electromagnetic calorimeter, and the trajectories in the tracking calorimeter are relatively straight. The other reason why at higher energies we can't work with satellites
because the particle flows are very low.
Das ist ein bisschen blöd, also diese Satelliten sind ja sehr klein, da
these
wird man einfach
satellites are very small and you won't be able to measure anything.
im Sinne von Statistik.
And that's not very practicable. That's why you use for high energies a different way of detection. That's something you do on Earth. Before
Tatsächlich auf unserer Erde aufkommen,
these particles arrive at Earth, they interact with the air molecules in our atmosphere. And what happens? It's some kind of air shower. So a cosmic radiation particle hits the atmosphere and interacts with the molecule in the air. And then there will be like a whole zoo of particles like mesons and muons, also photons and also light. This here, you can see it here very artificially. It's a whole network of particles, and these secondary particles, these are the ones you measure on Earth. And for this reason, that's a particle from some observatory. That's the largest observatory that does this nowadays. They just installed water tanks, and these water tanks, they put cameras. So what you measure in these cameras is the Cherenkov's radiation of these secondary particles from these air showers. Cherenkov radiation, I'll talk later about this more in detail. So just keep the question. Hey, what's that? Just wait. So, besides these water tanks, they also have fluorescence telescopes that they use for calibration. And these telescopes, they just use the effect that this whole air shower moves through the atmosphere and the particles interact all the time with the particles in the air and excite them. And what happens in the emission is fluorescence, and that's something you can just see with classical telescopes. Additionally, they'll get an upgrade. They'll get scintillators on top. They already started that in order to detect electrons a little bit better. And for completeness, there's not only RG, there's also a telescope array up there in Utah. That's sizably smaller, but they'll also get an upgrade, in particular more detectors. And interestingly, they're still a little bit smaller than the other, but I don't know why they didn't make it larger, but that's okay.
Wir haben also neuartige Methoden,
So we have new methods
kosmische Strahlen
in order to detect these cosmic rays, and that's why we can already say a lot about it. We already measured quite a lot. So what I'm showing you here is the results that you know in general. On the left side there's a particle flow, and I brought this in order to demonstrate why it wouldn't work with the satellites. So on the x-axis you can see the energy. That's in electron volts. That's a weird unit, but it's normal for particle physicists. An electron volt is the energy a particle gains if you accelerate it with a voltage of 1 volt. So for illustration, I showed the energies that you get at the LHC. On the y-axis, you see how many particles per square meter per time unit arrive at the atmosphere. So you can see in the blue area, it's a lot. That's 1 particle per square meter per second. That means, like with my square meter large satellite, you still measure quite a lot. On the middle of the red area, 1 particle per square meter per year, and all the way to the right, 1 particle per cubic kilometer per year. And that's when you need like the detectors, like the Berger Observatory that has just like 3,000 square kilometers.
Neben der Information, wie viele Teilchen.
Next to the information, how many particles according to which energy, we also have directional information. So on the right side, you can see the direction of at arrival of the particles. If you wonder why it's black at the top, well, that's because Auger is down in Argentina and they can't measure to the north. They can't see that. And you can also see this dotted line. That's the galactic plane, and the center is the star. They measured from which direction in the sky they measure more. And you can see more particles arrive in the bottom right. That's what's greenish. So one could say, okay, I know now where they come from. Then I maybe can answer what are the sources of the particles.
Man weiß ein bisschen was über die Quellen.
One knows a little bit about the sources. One knows that at lower energies, so if you go back to the plot on the left, the blue stripe, that's basically all solar cosmic rays. They come from the sun. One has verified that by looking at how does it correlates with what we measure with the activity of the sun. In the middle, like in the red area, these are the particles mainly from our galaxy. How do you know that? Well, you don't know that 100%, but one knows, well, cosmic rays, they are charged particles. They're like 90% protons, 9% helium atoms, and the rest is like more heavier atoms and some electrons, positrons, and such. But they're all charged. And these charged particles, they get deflected by magnetic fields. For example, in our galaxy, I just really think these pictures are very beautiful, and the path these particles traverse, the curvature depends on the energy. And now the lower particles, the galactical magnetic field, causes that these particles don't leave our galaxy. And the probability that they leave our galaxy is extremely low. So before that they would interact, and it would be billions of years until they're caught in our galaxy.
At medium energies, our cosmic rays are likely from our galaxy. At the highest energies, however, the particles are capable of leaving the galaxy. And these curved trajectories are the trajectories you see there of the highest energy particles. At the highest energies, we know that cosmic rays come from anywhere far away, from a galaxy far, far away. In my talk, I'm going to talk about the highest energy cosmic rays from a galaxy far, far away. Outside our galaxy, there are a lot of objects. There are strong objects, gamma bursts and black holes, and outside our galaxy we still have the problem that the cosmic rays is deflected by magnetic fields, and that the direction of impact, the direction of arrival for the highest energies, it can't be traced in a straight line to the sources. So it's even 100 years after these first balloon flights, it's not clear at all where these particles originate. We examine this, but we're trying to use other particles too, because our universe doesn't send protons and helium-4 alpha particles. And for this search of the sources of this high-energy cosmic radiation, you could take the standard approach. We look at what is particularly bright. We look at the photons that are emitted from the universe. And the nice thing about light is that we know light from every day, but light as information source is extremely versatile. You see the galaxy in the optical range here, which you can see with your eye if you look at the Milky Way, and this is already quite impressive. But electromagnetic radiation has a lot of other wavelengths in ranges that our eye can't detect. And if we look at the Milky Way in all sorts of wavelengths, we get a much more diverse picture of this object. And one can get a lot more info and extract much more information. And the nice thing is each wavelength range tells us something about different properties of the Milky Way in this case. For example, in the radio range, you see emission lines of atomic hydrogen. So you can do by radio astronomy, you can look at warm clouds of gas that have lots of atomic hydrogen. And you also see the molecular hydrogen, H2, in the radio range, and you can look at somewhat colder dust clouds. In the infrared range, you can dust is emitting light that's excited by starlight and then re-radiates in the infrared range. And at the highest energies, we have that was really interesting us. We are looking for the sources of these highest energetics cosmic rays. Those are charged particles at a very high energy, accelerated to a very high energy. And in this, and while they're accelerated, they are radiating all the time. When they get deflected, when they interact. So in the X-ray and the gamma ray range, you get those could be those give us hints what the sources of the cosmic radiation are. So they could, but there are diverse problems with light. The first problem is at the highest energies, the light doesn't get very far in our universe. There's something like the cosmic background radiation, and that fills our entire universe. That's a relic from the primeval times of the universe, when the universe was opaque and suddenly it became transparent, and that gave the microwave background. And from a certain energy, the photons interact with the cosmic background radiation, and then they don't appear at the Earth anymore. And that means you see it in the graph to the right, where you see the energy of the photon in the x-axis, and the y-axis is how far the photons get. And what you see is that at 10 to the 14 or 10 to the 15th electron volts, the photons go only to the galactic centers, a few kiloparsec, and that's just not far enough. So if we want to get cosmic rays from galaxies far away, it's just they don't get far enough. the light doesn't get far enough. So light as information carrier, high energetic light is an indicator of high energy particles, but those don't have to be protons or helium cores necessarily, so it could also be electrons. So it's not unique. We can't uniquely discriminate what the source that produces cosmic rays. And the last practical point is that if I want to measure light, and it has to be dark, and on the Earth it's a problem, and the telescope needs to be oriented correctly, or we have to use satellites, so it's just not very good, very accurate. So are there other carriers of information too, which we can use in our search for the sources of cosmic radiation? And now we get to the third messenger, to the neutrinos.
Ich möchte jetzt einen kleinen Einschub machen.
Now I want to put a little insert or standard model. In contrary to protons, that's not in everybody's mind. So it's a short excursion into the standard model of particle physics. The complete matter is built out of leptons and quarks. Of leptons and quarks of the first family. Up and down quarks, and protons and neutrons, and those form the nuclei of atoms, and around them are electrons, and so we get our atoms, all of our atoms. And up and down are quarks, and there's also on the leptons there's the Elektron-Neutrino besides to the electron. There's not just the first particle family from which the matter around us is. There are two more versions of this. They're the same in terms of charge, they're just heavier. In each of these particle families, there is a neutrino. Neutrinos don't constitute our matter in that sense, but in radioactive beta decay they are important, and they play an important role. What properties have neutrinos? They're not charged. They have almost no charge. 3-4 years ago, there was a Nobel Prize for the proof that neutrons have finite mass, that they don't have zero mass, but it's still infinitively small. Infinitesimally small, and they only interact through a weak interaction. That's why they're often called ghost particles. And how weak this interaction is you can visualize by thinking about how many neutrinos impact the body
per cubic centimeter per second. That's 65 billions of neutrinos, and obviously you don't notice that. So that means the interaction is really non-existent, or only very rare. So now we know what neutrinos are. Now we need a connection to the cosmic rays. Now, if in astrophysical sources there are cosmic rays, then they interact with other cosmic rays, as with other protons and helium atoms, or with light. And from this interaction, there will always be, in principle always, very often, you'll have neutrinos. They have 5% of the primary energy. So if you have a very high energetical cosmical rays, like we're talking about, then we'll have also very high energetic neutrinos, but like of a factor of 100 less. But in contrary to light, that means that if a source emits neutrinos, then it's very certain that they're also cosmic rays. Because if not, then there would be no way of them being created. So they're a jackpot for our work. So they can travel extremely far because they interact very scarcely. And it would really prove that there are really cosmic rays in these sources. So we want to measure neutrinos. And that's a little bit complicated for the same reason that they get so far, because they rarely interact. So I want to present here one detector, that's the ice cube detector. In principle, that's the neutrino detector for very high neutrino energy and has the highest sensitivity. For low energies, there has been a talk here on the Congress, but I think that was on day one.
That was Kamiokande.
There are also other detectors that cover these high energies, for also in future, so I want to name them. That would be KM3net. That's being built in the Mediterranean. And but for now, we concentrate on the ice cube detector. It's a detector that's 1 cubic kilometer large. That's an incredibly large project. Over 250 scientists are in there, and that's a beautiful example for a project that's crossing borders. What IceCube does, it detects the Cherenkov's radiation of interacting neutrinos. So you never detect the neutrinos themselves, but you detect the leptons that come from the interaction with a neutrino. So on the bottom right, you see I want to explain this picture. So you have the electron neutrino that comes in the top left, and that interacts with a neutron in the bottom left. They exchange an interaction particle, and what happens, the electron neutrino turns into an electron, and what I measure is this electron and the Cherenkov radiation of this electron. So now an excursion to what is Cherenkov radiation.
Cherenkov radiation is a sonic boom, but for light. This is if a particle in a matter propagates faster than light in matter that's possible, then Cherenkov radiation happens, and it's still the particle is not faster than light in vacuum. It's only faster than light in the matter. It's still slower than the vacuum speed of light. This is still the hard speed limit. We also know this from nuclear reactors, which is the upper right picture. The blue glow, that is the same effect, that's the Cherenkov radiation. So if we want to detect an electron neutrino, how does that work? The electron neutrino gets into the detector, it does an interaction. There's an electron, and the electron produces Cherenkov radiation, and we want to detect the Cherenkov radiation. So they built a giant detector for that, 1 cubic kilometer, and lots of cameras that detect that blue light of the Cherenkov radiation. 5,160 cameras on ropes, and every 17 meters there is a camera module for blue light. Those lines are built with 125 meters distance, and it starts from a depth of 1.5 kilometers and goes down 1 more kilometer. There are not only these 86 wires or strings that are spaced 125 meters apart. At the very inner bits, there's a core which is spaced tighter to do other deep core. There's to do other measurements, and on the top there's in principle a detector like the Auger Observatory. Those are ice tanks to detect cosmic radiation. IceCube, like Auger, wants to do an upgrade. They want to increase the volume by a factor of 10, and they want to do some improvements to the deep core in the middle of the detector. So we want to detect this Cherenkov radiation, and for that, every 17 meters on some strings there are optical modules, and it's so impressive how this is built. So I brought some photographs. You need to imagine that you need to drill 2.5 kilometers deep into the ice, and how they did it, after they drilled through the snow. For the ice itself, you use hot water drills, because if hot water meets ice, the ice melts. So in principle, they got a column of standing water, and into that standing water columns they lowered their strings with the detectors, and that worked extremely well. From 2004 to 2010, they built this. And obviously, you never can retrieve the digital optical modules if one of them fails, but more than 98% of these things are still functional. This is really impressive. This is how it looks. This is all under extreme conditions. You're on the South Pole in the Antarctic and try to build a giant detector. That's really impressive. So if you would stand in the ice, this would look like something like that. And before we deal with the neutrinos, how is such an what comprises such an optical module in principle? These digital optical modules are just cameras for blue light. The card is the white blob you see on the picture to the left. That's a photomultiplying tube.
Das heißt, da fällt einfach Licht aus.
If light impacts, it's transformed into electrical charge. I want to show you two interesting things. This mu metal grid to shield the Earth magnetic field. There's a mu metal grid. And what I found extremely funny is this flasher board left in the graph. So each of these digital optical modules, besides the main board that does the data acquisition and sends data up, it has a light source in itself by which it can generate flashes of light to calibrate the adjacent module. So these digital optical modules measure the Cherenkov radiation, and we look at how this looks if an electron-neutrino goes into the core. It does an interaction, an electron is produced, and the electron does Cherenkov radiation. So in the video links, you see what the light signal looks like in the ice. On the right side, you see how the detector perceives that. So left is something starts. That happens when the electron gets produced. And the special thing about electrons is that they interact all the time while they interact with the ice, and you get a whole shower of electrons that make a Cherenkov cone, and in the end there is a big sphere. Right. Okay, that was visible on the right what it looks like, but now it's already gone. In the next picture, it's shown as blobs attached to the digital modules, to the camera modules. The bigger the blob, the more energy has been deposited in that volume. And the color code is a time code. It shows when light was measured. So that's what it looks like if an electron-neutrino impacts. If a Myon-Neutrino impacts the detector, it looks different. Myon-Neutrinos produce muons and not electrons, and muons don't interact as nicely as electrons. They have a longer lifetime, so they just go through the detector on a relatively straight line. They leave a relatively straight trace, and you also see that straight trace in the digital modules on the right side.
Man kann sich auch direkt schon denken, was die Vor- und Nachteile dieser
You can imagine what the advantages and disadvantages of these particles are. So muons have a extremely good angular resolution at 0.2 degrees angular resolutions, but these muons fly out of the detector, so they're already coming from the outside sometimes, so they deposit a part of their energy outside the detector, so you cannot catch the entire energy and take and find out how much energy is deposited as opposed to the electrons where the sphere deposits the whole energy in the detector, but the angular resolution is very bad because this looks very nice, but the biggest problem in reality is the background in the ice cube. Ice cube measures about 10 astrophysical neutrinos with this extremely high energy that we want per year. So in 1 year, at the same time, they're measuring 100,000s of atmospheric neutrinos and 10 billions of atmospheric muons.
Es ist einfach ein wahnsinnig großer Hintergrund.
So there's an extremely high background in the detector. So in reality, if you look at 10 milliseconds in the side of Ice Cube, this is what you get, is that it's highly impressive that you get any useful data out of the background here. And the green lines, the impinging green lines are atmospheric muons. So there are different veto systems. So you only take events that already went once through the Earth until the impact on the detector. So you sort out atmospheric muons, or you define the outside layer of the detector as veto. So what happens in the veto region we don't accept as an event. So you can use atmospheric muons. So then if it's in the atmosphere, so okay, at 300 tera electron volts, there's almost no atmospheric neutrinos anymore, so you're relatively certain that this is the real thing that we want to see. So actually, Ice Cube has identified some neutrinos as astrophysical neutrinos since 2012. The first big success was the first 28 neutrinos in
Und bis heute hat man so Größenordnung 100 Neutrinos gemessen und man kann so schwer
until now we have measured about 100, so you can do some things like we can draw how many neutrinos per energy interval we have. But now we also have built this detector because we want to find the sources of these high energy cosmic rays. So what are the sources now? So what you do is that you usually look, okay, I measure one of these neutrinos, and I see, is there, in this direction, is there like a very strong known astrophysical object like quasar? But we didn't find anything in these directions. So we found this whole new flow of astrophysical neutrinos, but up until now we didn't know where did they come from. So more of a additional riddle than solving the question we posed. So, and that's where we get to now what's been published this year. So the first time a neutrino has been measured, and we could identify the source of this neutrino. So this neutrino could be identified to a blazar, which is known from measurements of photons. So in our world, this looks like this, these news. And of course, much more of these. And of course, I added the Nature Astronomy article of our work group and not any other source. But the main part to take away from this is we measured a neutrino, a very high energetic neutrino. And this neutrino could be, this neutrino came of the direction where a quasar is, that at the same time was also very active. So a simple excursion. What is a blazar? In principle, it's the core, the active galactical core of a galaxy very far away. It's a supermassive black hole. And it has a jet, and this jet is pointed towards the Milky Way or the Earth.
Ich möchte da jetzt noch mal kurz ein Wort zu sagen.
I want to say another word to this. So these active galactic nuclei, there's lots of words for these. Don't get confused by these. They're all historically term from history-wise, and real blazar is just an active galactical core with a jet that points in our direction. So these blazars have very characteristic radiation in their electromagnetic spectrum, and every couple of years they become active and stay excited for a couple of months. What exactly is this radiation? That's a little bit more complex. And these two videos are also from DESY, my institute. and that it made there, and along this discovery, they were made. So how does this core look from up close, and what does emit radiation? So first you have this black hole, and there's this disk around, and this disk emits light in the ultraviolet spectrum, and the radiation that leaves they heat up clouds that are above this disk. So these clouds become excited and emit line emission. That's the so-called broadline region, and they are very wide, just because these clouds move, and the Doppler effect widens up this radiation. And around there is a dusk torus, and that's that covers up most of this. And most of all these cores have this jet that is powered from the accumulation of matter and moves with relativistic velocities. Within this jet, there's turbulences that cause particles to accelerate, mostly electrons and protons, and these particles they emit electromagnetic radiation. That's what we can see. So back to our discovery. On the left, on the top, you can see this one neutrino event that has been measured, and it's very remarkable how this happened. They have this alert system. It's a Myon-Neutrino, so it has a very good energy we can reconstruct. So they published an alert. Hey, we have this 300 tera electron volt neutrino. Please point all your telescopes, optically, X-ray, whatever, in this direction and see if you can find something. And indeed, they found that for the first time, from the same direction that this neutrino came from, there's also gamma rays that have been measured, in particular from a blazar that's been known for quite a while, and it's been active for quite a couple of months already. So additionally, what they did, IceCube has been since 2012. The accumulated data has decreased. Okay, it dates a little bit farther back than 2012, because before the detector was finished, they only had some parts of the detector active. And in the meanwhile, they found that in the period from 2014 to 2015, there has been another accumulation of neutrino measurements from the direction of this quasar. So about 10 to 15 neutrinos. Along the lines, I want to say add a couple of things. Within this period between 2014 and 15, this blazar wasn't more active than usual in terms of gamma rays. It was just very calm, but apparently it emitted more neutrinos. So during this event in 2017, that's shown in the top, a lot of our is very nicely explainable with the models we have, and also be able to simulate. So this historical flare, that's what we call the emission in 2014 and 15, was quite a bigger challenge. So with the models that we have, we need quite cross parameter fine-tuning to be able to explain this. Also, I've seen models that try to explain this by saying there's probably a star that flies into this jet, and that's the source of this neutrino production. So you need very exotic models, and you have quite some difficulties to explain this increased activity. But what remains is that for the first time we've been able to possibly identify the source of a neutrino. I want to highlight two of these headlines. So what does this mean? It means not what's said on the left. It doesn't mean that we found the mystery space, the source or the origin of the mystery space radiation, but we found one possible source
ein Neutrino
that
emittiert hat.
possibly emitted one single neutrino. It doesn't mean that all neutrinos come from pulsars like this TSX. In reality, their account is very limited.
Es ist außerdem so, dass wir dann als Rückschluss
Furthermore,
daraus
we can learn from that. In this one source, there were possibly protons, but it doesn't mean that all cosmic high-energy rays come from this source or only come from sources of this kind.
bedeutet das alles nicht.
That's not what it means, but it's a start, and that's the first time that with these large neutrino detectors we can do astronomy.
Und in dem Sinne,
And in this
das weiter
sense,
unten auf der rechten Seite,
the headline on the right,
das trifft es schon eher. Es ist
that's a
ein
little bit closer. It's a little bit closer to home.
Das, was damit
It is a
begonnen
breakthrough.
hat, wird mit neuen
Because
Observatorien,
what
CTA gebaut
what
wird,
this
mit
started with
Upgrades,
upgrades and like for Ice Cube,
weitergeführt werden.
it's going to be
Es werden mehr
continued.
Messungen dazukommen.
We're going to have more measurements. We can improve our models,
Und dann hoffentlich in
and
Zukunft
hopefully in the
irgendwann die Frage
future
beantworten
we'll
können,
hopefully be able to answer the question, where do cosmic rays come from?
Dankeschön.
And with that, I thank you for listening.
Anni, eine Punktlandung.
Alter, ich bin selbst
Well,
erstaunt.
it's a touchdown on the spot. Aesthetic pictures, nice colors,
Vorgetragen.
calm talk, and very calming talk.
Gerade wohl verpasst hat.
What Sifa just missed, we have.
Was hast du gelernt, Henning?
We
Das,
have
wenn du
learned
vorher
something
gesagt
that
hättest,
if you had said before, fluorescing telescope, that's a telescope that glows in the dark. So it's a fluorescence, not a fluorescent telescope. So we have open microphones. Just line up and people stand up all the way in the back. Signal Angel waves. We have a question out of the internet.
Schieß mal los.
Just shoot.
Hi.
Hi.
Zwei, drei Folien vorher.
So 2-3 slides ago, you had this graph about the temporal evolution.
Die Frage, was der Gap.
This is the question: what is the gap between 2015 and 2016?
Tatsächlich,
In
das
fact,
ist ja nur eine Analyse.
this is just an
der
analysis.
Gap. Also,
So the gap,
um ganz ehrlich zu sein, müsste
to
ich
be
selbst
quite honest, I'd have to
nochmal
look
nachlesen
read up in the
in
have to
dem
read up
Paper.
in the
Ich nehme,
paper.
aber also das ist ja nur
I'm
ein
assuming
Gap, der
that
in der
it's just a gap in the analysis. So they did two analyses. So they did the Gaussian analysis and the box-shaped analysis, and maybe they limited their time window.
Aber genau weiß ich es auch
But
nicht.
I
Es ist auf
don't know
keinen Fall
exactly.
irgendwie ein
It's
Messgap, sondern
not a
in der,
measurement gap, but it's
in der Interpretation danach.
it's an artifact of the interpretation. Well, I can't really answer exactly. I know it even less.
Dankeschön. Das
Thank you.
Internet applaudiert.
The internet applauds.
Gehen wir doch mal rüber auf Mikrofon 2, bitte.
Hallo. Vielen Dank für den Vortrag. Der war
Thank you very much for the talk. It's a very nice talk.
Frage, du hast
That's my
gesagt,
question.
Neutrinos
So you
etwas
said
langsamer
neutrinos
sind.
are slower than light.
Wenn wir jetzt so ein Neutrino
If we
detektieren, haben wir
if we detect
sozusagen
such a
die
neutrino,
Chance,
do we have the chance
vorher, von der Quelle
to know
über Licht oder über Gravitation
to know from the source with using light in our lifetime?
Die sind so leicht, die fliegen
So there,
Lichtgeschwindigkeit.
that
Ja, ja,
light
auf jeden Fall.
that
Das
they
muss
fly
coincident
is essentially the speed of light. So they have to be coincident. So the minuscule difference. So the masses are the neutrino masses are so minuscule that they're basically measured, detected simultaneously.
Möglich. Wir schalten jetzt in den hinteren Bereich des Raumes auf Mikrofon.
Technology makes it possible to switch to microphone number 4.
Are there any possibilities to influence
ein Neutrino durch Masse durchfliegt?
whether a neutrino flies through mass or interacts with this mass?
Also,
Nope.
das ist einfach ein
So
Wahrscheinlichkeitsprozess.
this is just a probabilistic process. You
nicht
cannot
beeinflussen. Du kannst
influence
natürlich
that.
mehr Materie davor
You
bauen,
can
in der
put
Hoffnung,
more matter in front of it in the hope that more matter
dafür sorgt, dass es früher interagiert, weil es
makes
ja früher auch mehr
leads to
trifft, aber
earlier
das ist
interaction. But not in principle. No, not with neutrinos.
Scheint, als ob alle Fragen beantwortet werden.
All questions seem to have been answered.
Sag mal, war das eigentlich dein erster Talk für so eine
Was that your first talk for such a big crowd?
Dein letzter Talk
Yes.
für so eine
Was that your last talk in front of such a big crowd? Next time, if my colleague isn't in Shanghai, I might give it again.
Anni!
So that was Anni.